I assume that you can hear us from home. It is our pleasure to have here Karsten today. Karsten got his PhD at Aarhus University in Denmark, and then he held several postdoc positions around the world, including one position at Birmingham with Andrea, and several other positions as a lecturer and assistant professor. And since December, he's here a postdoc at the University of Bologna, working with Andrea Miglio, and his science interests are eclipsing binaries and stellar clusters with the aim of obtaining more accurate ages for the stars. And today he's going to talk about open clusters in the Kepler FOV. And we look forward to it. So please.
Thank you. Thank you. So excellent presentation that leads directly into what I'm going to talk about today. Maybe not so surprising. So today I'll be talking about the open clusters that was observed by the Kepler mission. And I'll try to sort of show what has been done and what we're still working on with that, and how this leads on to another mission that we really would like, namely the Haydn mission, and how this is connected and still maybe not directly, but indirectly anyway. So just to make a brief outline of what I'm going to say, it's not a long talk, so I will not make a long effort in this. Just to say that all this work is related to my main question that I want to answer, namely how accurate stellar ages can we actually determine in various cases. Not how precise, how accurate, meaning how good is the models. And the secondary goals, of course, is that along the line of this work, we'll learn a lot of details on stellar physics, star clusters, and our galaxy. So the tools that I'm using is the test eclipsing binary stars and asteroseismology. If I can, I would like to do this in clusters. That is the topic of today. So for stars in clusters, I would like to use the tools of asteroseismology and eclipsing binaries. And specifically, these are the tools. In this context, you don't really care too much about eclipsing binaries as a concept. You don't care much about asteroseismology as a concept. I want to use these as tools to learn something about the stars. And specifically, the main goal is to know the accurate ages. So what we're going to look at is then the Kepler open clusters, what we have learned from them, and what we're still investigating with those, and how we can then extend these investigations into the Haydn mission later. So I already had a go at this. So the main goal here is to figure out what is the accuracy of the age that we can obtain for stars, not the precision. So we know from stellar models, hopefully a little bit better than the one shown here, that if we know the initial mass and we know the initial composition of a star, then at some later time, if we take a stellar model, we can obtain the luminosity, temperature, and radius as a function of a t here. And if the model is accurate, then this t means the age. If the model is inaccurate, then this t has no meaning whatsoever, and then we don't really know what we're doing. So what I really am after is how well does this t relate to the specific, really, the real time, not just some parameter. So the tools that we're using, the test eclipsing binaries, just to remind everyone why some people like them a lot, including me. If I have an observed light curve, and I have observed spectra, then I can combine all these measurements from the light curve. I can get relative radii only relative to the orbit. I can get an inclination and an orbital period. From the spectroscopy, I can get minimum masses, and I can get the orbit semi-major axis, but only coupled to the inclination, which luckily I can get from over here. And then taking all this together, I can get masses and radii very precisely and very accurately, because this has very little model dependence. There's a little bit on limb darkening on the light curve, and there's a little bit on 0 points on the radial velocities. But this is really just a geometrical model, and this is really just gravity as we know it. So there's very little model dependence. So that means that these parameters can be determined very accurately, not just precisely. Also, with modern method, we can beat down to the level of 1%. Some claim even better, but then things become a little bit more tricky. But at least we can get to a 1% level with these numbers, which is needed to challenge the stellar models. So having the mass and radius, we also have, of course, log G, which is just a combination of the two. And then if we take that and put into a spectroscopic analysis, we can get composition and effective temperature even better than we could, not knowing log G in advance. And then from these numbers, we can then calculate luminosity and therefore distance, or if we these days have a distance from, for instance, Gaia, we can know the distance and then check whether the luminosity is consistent among what you get externally and what you calculate from the system. So this is probably, at least in my claim, this is the way to measure very precise parameters in order to challenge stellar models. And then you would think that, well, then we would just look at all the eclipsing binaries we can find, and then this will be enough to challenge the stellar models. But actually, even in this case, where we do our very best, if we do this for stars just in the field, there's still not enough information that we can actually test whether our model is correct. We can use this to get a very precise age for any given model, but we cannot really select among different model physics. So in order to do that, we have to do something more, which is why we want to study these systems in clusters. So the other tool is asteroseismology, and I will not give a long lecture on asteroseismology here. Today, I will take the empirical approach, just say, we have this thing that if we have a light curve of these oscillating stars and we transform that into a power spectrum, then there are two parameters, which are known as delta nu, the large frequency spacing, and nu max, the frequency of maximum power. And magically, if we take those and combine them, we can get an estimate of the mass and the radius of these stars. And of course, then, if we want to have this to actually work, not just roughly, but very accurately, then there's these annoying correction factors that depends on the model physics that we have to take into account. So that's another story that I will not tell you about today, but just say that we're using these tools and then trying to test them along the way as well. Okay, so for the observations, so doing asteroseismology takes long, uninterrupted light curves. So the Kepler mission was excellent for doing that. Unfortunately, there was only 4 open clusters in the Kepler field of view, so that's the ones that we have been looking at, we'll be looking at today. So these are the clusters from young to old. So starting at the old age, we have NTC 6791, probably 1 year further off before if you study open clusters, and then going to younger ones and even younger one that is the latest that I'm working on. For these clusters, apart from doing asteroseismology, the good thing about having long uninterrupted light curves is that you can find eclipsing binary stars very easily just by looking at the light curves. So many of these clusters have now quite a few known eclipsing binary stars that are members, except unfortunately the youngest one, which still hasn't had any eclipsing binary star found. But we have eclipsing binaries and we can do asteroseismology in all these clusters. And don't mind all the parameters, those are the ones that we are really after fine-tuning along with this work. So the idea with a sample like this is that, of course, we would like to get the most accurate and precise ages for these stars and calibrate the model physics if we can by having all these combined constraints at the same time. So let's look at what has already been done. So if we start with the oldest cluster, NTC 6791, I had the pleasure of studying this cluster in great detail. So in this system, we had 2 eclipsing binaries so that we could match isochrones to the mass radius diagram simultaneously as the CMD. As I've put here on the slide somewhere, the isochrones in the CMDs here are not a fit to the observations, they're just matched to the luminosities of the binary stars. And other than that, it's all matched in the mass radius diagram mainly. And then the only thing that we use the CMD for is then to match the turnoff and the subgiant branch in order to be able to adjust more model physics than you usually can when you match cluster CMD. And in that way, we were actually able to constrain the helium content of this cluster at the same time as the age. Good. So for this particular cluster, which is very old and very metal rich at the same time, it's had a long line of studies showing in the early days that it was special in so many different ways. And the more we study it, the more normal it seems to be. So one of the things that is still interesting is what is the specific detailed abundances in this cluster. And unfortunately, that's one of the things that every time there's a study, you get different numbers. So the abundances, not only iron, but also the alpha elements and stuff like that, is very uncertain in this cluster still. But one thing that I found at some point, looking at other stars observed by the Kepler mission, I found a field star which had also had a spectrum that looked exactly like one of the stars in the cluster. So this is the comparison here, the dotted line and the black line is two different stars, and they look, at least to my eye, extremely similar in this context. So it seems that no matter what the detailed abundances is in this cluster, it seems that it's not something that you don't find in the field. So I said there was many eclipsing binary stars found now in NGC 6791. The reason I know is that's because I found them. So I looked through all the single pixel light curves, all 40,000, one at a time, just to make sure that the automatic methods didn't miss something. So these are the eclipsing systems that I found. And for many of them, we also obtained spectra with flames at the VLT. And a lot of that work is then still, as I say here, still ongoing, because it's not so easy with spectra from flames to actually get very accurate parameters, at least not for when you get down to this level of magnitudes. So among those systems observed with the VLT, we also found a non-eclipsing system, B56, which is shown here in the CMD, and you can then use the light ratio you get from the spectra to separate the components out. So you have one down on the main sequence, which is nicely placed between the two components of another eclipsing system, so that we know the mass here, and then if we interpolate through these, we know the mass here, and then we can also predict the mass up there. And if you put that in the same mass radius diagram as for the other two systems, we still get an extreme consistency, even if one system is now up on the subgiant branch. So that gives confidence that the earlier predicted isochrone was the right one. And also another thing it shows is that if you have eclipsing binaries, they actually are similar in mass and radius to the single stars, because that's one of the objections that are sometimes here, that, well, a binary star, they don't evolve like single stars. But this shows that, well, in this case, it does seem to be working that way. And if you're still not convinced, then there's also actually now a giant component of an eclipsing system, which is further up, and still the mass is very consistent with what you predict, even for the giant stars in this cluster. And now we're extending into the region where it's unlikely to, unfortunately, find too many eclipsing systems up here, but now these stars marked up here are now the ones where we actually have asteroseismology. Which brings me back to the same work I showed earlier, the two eclipsing systems and the cluster CMD, because this was also actually the first test of asteroseismology back in the early days. This was 2012, where the scaling relations had never really been put to much of a test. And there were two papers from asteroseismology, one from Andrea and one from Sabani Basu, and both of them got masses that were higher than I would get from this isochrone that I scaled to see what is the mass of among the RGB stars. So at that point, there seemed to be some kind of inconsistency here. But as I put in that paper, it's really not so surprising, because these were just very early days of asteroseismology, and it was just the raw scaling relations. And no attempt had been made to actually see what the details of asteroseismology would do. And if you take into account the corrections that we know these days from asteroseismology, then this number here is completely consistent with what you get from asteroseismology. So this was both the first test, and later on it's also shown that asteroseismology is actually accurate to a very high level. Okay, so including the asteroseismology, you could learn something more about the cluster that I couldn't get from the eclipsing binary stars by itself, namely the mass loss on the RGB. So this is the same figure again. So we measured asteroseismology of the RGB stars and in the clump phase, and then compared those two masses to see how much mass did the stars lose high up on the RGB before reaching the clump phase. So this is the first direct way of actually measuring how much mass did these stars lose. And interestingly enough, in the literature, there's been so many discussions of how this very high metallicity open cluster would have a very high mass loss. And what this paper showed was actually that no, the mass loss is actually quite low and much lower than it is in the globular clusters. So another thing that was at some point in time weird about this cluster is that it had these very hot stars out here that were members, and then the rest of the helium burning stars are in the clump here, and then there was something in between, which was then some authors were tempted to then claim that this is the link that couples this to this. So these are the blue horizontal branch stars of NGC 6791. So the only issue of that is when you look at this figure, if you don't color these points blue and then instead you draw some lines up here, then you can clearly see that these are probably just blue stragglers. So of course, this is very strange just to couple these in this way. And that's also what we looked at in my work in 2012, is that if you plot these stars, some of them are here in blue again, and then you actually also put on some isochrones, and you put the horizontal branch, then you can see that, well, these fall below, way below what you'd expect for the luminosity of the horizontal branch, if there were any very low mass horizontal branch stars in this cluster. So these are probably just blue straggler stars and nothing special. The only issue is then what are these guys over here then? That's the interesting part. At this point, there was also some astroseismic studies showing that, well, there was one of these stars among the clump stars, which from astroseismology was actually identified as an RGB star. So what was that doing there? So that might be then related to these guys here. And in the meantime, actually also astroseismology was measured for these stars down here, and shows that these are actually oscillating extreme horizontal branch stars. So they are real somehow, and they lost a huge amount of mass, so they must be somehow related to binary evolution. So recently we also managed to do asteroseismology of some of the remaining weird stars up there, and showed that if we look at them in a mass distance or a mass parallax plot like this one, then all the stars are at the same distance, but some of them are actually overmassive. So these are some of these stars that you see in open clusters that are more massive than the common RGB stars. And this has to be related to binary evolution. So they must have been blue stragglers at some point and then evolved to the giant phase. And then we also, along these, we also found a group of stars that seemed to also have a common distance, which was not the same. And they also fall in a very low mass range. So one speculation in this paper is that maybe these were stars that at some point in time, a long time ago, belonged to this cluster, and then they were just lost due to interactions with the rest of the galaxy. But this has to be investigated, and unfortunately at this time, there's no optical spectra of these. Of course, somebody has to observe these at one point and see if they also have the very high metallicity of the cluster to verify whether this is right or not. And you might think that we're done now, but there are still stars that have not been observed and analyzed through asteroseismology, even though they have data from Kepler. And one of them that we've looked at recently is this one, which is studied in a paper where they say that this is a very special star because it has extremely high metallicity. And the preliminary analysis shows that, at least for the stellar parameters, the star is not special at all. So maybe there was just something wrong in this case of this analysis. But there's something more to be looked into there. So one of the things that seismology has also shown, unfortunately now we can't see the title up here, is that you can actually also, with asteroseismology, you can also measure the helium content of stars. You cannot do it very accurately, but if you have an ensemble of stars like you have in star clusters, if you combine all the individual stars' results, then you can maybe do a better job of that. And there has been this paper showing that, well, actually for NGC 6791, you can measure the helium content of these stars, and surprise, surprise, they get the same result as I did with the eclipsing binaries a long time ago. The only thing is that when you read the paper, you can't see enough details to know what they actually done. And if there were enough differences in the model physics investigated to know whether they actually, this is a valid result. So this is something that should be investigated in much more detail, because if this is really true, then this is excellent news for the coming studies of more clusters, that we can then measure the helium content of the stars. Moving on to the next oldest open cluster, we did similar stuff. So this is work by Rasmus Handberg et al., including myself, where we also did asteroseismology of stars in this cluster, showing, again, comparing the mass and the distance modulus to predictions from an eclipsing binary, which is the point in the middle there. And then you have the asteroseismology. The red points are the perihelion burning stars. The blue points are the RGB stars that are also shown over here. So you have all the normal stars if you want here, and then you can see that there's also some overmassive stars that are here at the same distance but higher masses, and then there's also an undermassive star here, which I'm sure Massimiliano will tell you a lot about. If you ask him about that, I don't have time to go into the details. But again, we can measure the masses and get a good age estimate of the cluster, and we can find these special stars that did not evolve as single. And this same work could then also be used to, for the first time, show that the predictions of the corrections to asteroseismology actually works. So this is a diagram showing how you'd expect the difference to the correction to the delta nu scaling to actually go. So the blue is the prediction for the RGB, the blue points are the RGB stars, and the red is the same for the perihelion burning stars. So this was the first time we really showed just empirically that, well, the predicted corrections from the models, they actually seem to be working. So the next cluster, NGC 6811, we're now moving to younger clusters. This is about 1 gig a year. So the younger the cluster, the less the stars, unfortunately. So there were only 8 perihelion burning stars in this cluster in total. But on the other hand, we're moving into a regime where we're getting close to the transition between whether we had an RGB flash or not. And therefore, we can start testing different model physics. And in this case, we just had a brief look, not in very good detail, but just a brief look at seeing whether we could tell from this or prove from this that there had to be core overshoot in these models. So that is what is shown here. The red isochrone is the one without overshoot, and you can see that it doesn't reach down to the stars at the bottom here. So you have to put in core overshoot in the models to actually reach down. You can also see that the other models that have a standard amount of overshoot, according to recent calibrations, they seem to be maybe over predicting how much overshoot, because they go beyond what is actually needed to match these observations. So there's some indications here that you can sort of calibrate the overshoot parameter for mixing. And now again, you can see the title on top. I'm sorry about that. So this is NGC 6866, the youngest of all these clusters that has been observed. That's the work I'm doing at the moment. So here there's only 5 oscillating stars. And the interesting thing is here that you have to, when you look at these isochrones, you have to match. These stars are all from asteroseismology seen as being secondary clump stars. So that means that the part of the isochrones that should be fit by these measurements is from the bottom of these and going upwards, depending on which isochrone you're on. And you can see the cyan one is one of the good matching isochrones where you can more or less match all these observations, depending on how you define their uncertainties. And the blue ones are now models where the dotted one does not include rotation, and the other ones include various amounts of rotation, not in the core helium burning phase, but throughout the whole stellar lifetime. And what is seen here is that as you increase rotation, then you move up the beginning part of the secondary clump phase on these isochrones. So you move actually up so that you're way too high to match the observations here. And if you want to shift back down, then you can do that by using an older age. So you can go from here over here. But in that case, you still overshoot the radius by a lot. So there's no way you can actually match these observations with rotating models, at least not from these ones that are the Geneva rotating models. So it would somehow indicate that, well, these stars, maybe they're not rotating as much, but V-sin-I measurements at the turn-off actually indicate that they are rotating. So maybe it's just that we are not modeling the effects of rotation in the right way at this point. Okay, so in the end, what we really want to do is sort of try to build a test set so that we can use this to learn about ages of other star clusters, but also of field stars. And one way of doing this is looking into these new chemical age diagnostics. So this is a diagram showing the yttrium over magnesium for 4 different open clusters. And you recognize at least these 2 from what we've discussed so far. And you can see that these match nicely on some kind of relation derived for solar twins. This line is not a fit to these measurements. It's actually derived from other measurements. So calibrating such age diagnostics is another thing that is needed. And in order to make such a calibration, we need very accurate ages of the calibrating clusters. And there's been lots of studies on these. I'm just showing one specific one here, showing that we have various different chemical abundances that we can use to get an idea of what is the age of field stars. So the issue with these is that in order to make these calibrations, we need the ages to put into these. And at this point in time, this reference here has been used by a lot of authors because it's a huge catalog of ages of very many open clusters, probably the largest catalog there is. The problem is that it's potentially problematic because we know that there's specific incidences in this catalog where you get an age which is very far even from the training age that they put into the calibration. So the issue is that, and that's actually also the motivation behind my work, is that we can do a lot better than this, both from actually the way we're teaching the machine how to get those ages, but mainly from actually having a very good calibration set of open clusters that are well calibrated so that the model physics is calibrated and the age is calibrated at the same time, so that we have an input catalog of stellar clusters where we know this is the right age that we should get. And with that, this is sort of the conclusions of all this. The Kepler clusters has taught us a lot. It could have taught us even more, and we're still working on some of the details, but there's still something to be getting out of this. And the Kepler clusters were not alone. There's also, in the continued mission K2, there's also open clusters. Unfortunately, the K2 mission is much shorter, meaning that the time series data is much shorter, meaning that the quality of the seismology is much worse. And that leads us, of course, to why we need the Haydn mission. What we want to do here is the same. Specifically, we want to do asteroseismology in as many clusters as we can, both open and global clusters. And even though I'm mainly the one who's saying that, we also want to measure the eclipsing binary stars in those same clusters. Get combined constraints to have a huge set of star clusters where we know precisely what is the model physics and what is the ages of these stars. And this is, the way I see it, this is actually the only way that we can provide tight enough constraints to improve and test current stellar models. Because you probably all know that there are so many things even in current stellar models that we're not doing correctly. Just mentioning the mixing length parameter, we know now from 3D models that it's not supposed to be the same number as it is in the sun for other stars, but we still do it. Just because it's very difficult to put it into our models. And we also know that even such a boring thing as surface boundary conditions or T-Tauri relations is also something which is very problematic. And small changes to that can change the whole temperature scale. So there are so many things in the current models that we know is not right, but we really need a calibration set in order to improve on that. And Haydn mission is, as the way I see it, one of the only ways we can actually obtain that. And of course, we can move on and do something because we know that we could do a little bit in the globular cluster M4 with K2. And there's still some other open clusters in there. But as I said, the quality of that data is really not good enough. And we have problems with crowding that we don't have with the Haydn mission. So we can do so much better with a mission such as Haydn, where crowding will not become the issue. Yep, that was the last I had. Thanks.
Is there any question for the speaker? Also from I have one, but just because I'm in. What is a super stamp?
Yeah, the super stamps. Well, I didn't explain that. So the thing is that the way Kepler worked is that it observed such a large field of view that there wasn't time to transfer all the data down to ground. So the field stars were observed just by small images just around each star. But for the two oldest open clusters, we were lucky enough that they actually, instead of having just small images around each star, that took out 200 by 200 pixels centered on each of these clusters to allow you to go in and find all the fainter stars also in these images. And that is what also allowed to find the eclipsing binary stars that were not bright enough for seismology, but where you could still use the light curves for other science.
Any
beginning of your talk, you said that you were looking for the accuracy for accurate, not precise waves.
Yes.
And to go to accuracy, you need a reference that is the truth for you. What is the reference truth to measure accuracy of edges?
Well, that is one of the problems is that we do not have. But we can demand that for the parameters that we can measure, for instance, for the eclipsing systems, that for the mass and for the radius and the effective temperature and the luminosity and the chemical content, that all has to be matched by a model. And if you have a CMD, that also has to be matched by that same model. So that's the best we can do.
I agree with you, but this is a different definition of accuracy. It's some consistency. I understand.
Yeah.
But not,
that's
no more than
that's the only way of moving towards.
Not accuracy.
We're hoping that we are moving towards accuracy when we're having something which is that consistent. But I agree, it's difficult to know what is accurate. But at least we need to require some consistency in order to hope that we're moving towards accuracy. But in any case, this is exactly why this work is so important, and we need all these calibrating clusters, because in order to implement the model physics that we know is supposed to go into the models and changing mixing lengths and changing boundary conditions and stuff like that. If we don't have very accurate and precise measurements to test upon, then we will not know if we're doing something better when we're putting that in. And I guess that's the reason nobody's there to do it yet.
Any other questions?
So the calibration clusters you are using are those observed by Kepler or K2? Because I saw the names and the C1, 25, 6. So are they good in the K2?
No, they are not in K2 fields. They only have eclipsing prime resistance,
Okay.
but there's no seismology at this point in time. That's why I'm hoping as well that maybe Haydn will do that at some point in time.
Yeah, but I agree that the ages for some of the clusters that you showed are lower compared with the work that were found even by the older works.
Well,
Based on photometry of a single
there's quite a few
cluster.
things that in that work that you can question. But I think one of the major issues with that calibration is also that their precision is not very good. So even if they claim in the paper that relative ages will be good, when you take into account the precision on two clusters, then relative ages cannot be good because the uncertainties on each is enough to actually shift them relative to each other. So actually just the precision in that catalog is enough that it's a complication.
But there is a new catalog just out of the future a few days ago and there are many more clusters than that one.
Oh, interesting.
But I'm not sure that they did
I don't
Some-
they measure age.
they measure age.
Measure age?
They measure age, but in a few cases I looked at what they did and I'm not sure that they are better than because ages were not the thing that they wanted to measure.
Okay.
They wanted they want a compilation of all the clusters, open clusters and the strings and everything.
That's a science of.
Okay, just to have
Yes.
an idea. So they're going for
Science of photovoltaics.
But there are that is a much larger catalog.
Yeah.
Countries.
Yeah, but my feeling is that unfortunately that is also what people are looking at when they need something to calibrate. They look at what is there and what has all the clusters that I have, and then they care less about what is then the quality of that work, unfortunately, because there's other references. Because in principle, what you should do is just to look at what did this work use as their calibration clusters, because that would already be a step towards, that would be something which was more precise than they did. Because one of the curious things is that even if you look at what they get out for the calibration clusters, they get something out which is sometimes very different from what was put in. So that catalog is just troublesome for a couple of reasons. So people really should look for something which is at least self-consistent, rather than just having a catalog that has a lot in there. And of course, in the end, we all like a very accurate big catalog, but we all know that also that that's very difficult to obtain. So I guess in the end, I would like to provide that catalog sometime along the line, but there's lots of work to be done still.
Any other questions? No, I think we can wrap it up. Thanks to the speaker again.
Thank you.
Are you ready to speak?
Very well.